So today is May 19th. I'm just going to summarize what we have done so far, okay? And I have corrected the reports for lab 3 and logged the grades. That was your last chance to get credit for lab 3. Okay, I'm almost done correcting the reports for lab 4. I'll be posting the grades very soon. Third partial exam is the day after tomorrow. Chapters 22 through 26. Reports for lab 3 through 5. Final exam is June 9 from 9:10 to 11:10, okay? And what we did before, we were talking about the phenomenon of time dilation. Okay, the phenomenon of time dilation. And here is the notation that I used in my own notes, and here's the notation used in the book. Okay, this time that you see here, TCB, stands for period of the clock, measurement of the clock C as seen by referential B. Okay, and measurement of the clock C as seen by an observer in referential A. This time that you see right in here is referred as a proper time. And the notation in the book is delta T naught, proper time. Not in the other one, delta T is not proper time, time that's not proper. The ratio 1 divided by the square root here is appear very frequently in relativity. So we give it that name, we call it gamma, which is a factor always greater than 1. According to experimental evidence, we have never observed a massive particle traveling at the speed of the light. Accordingly, the only particle that travels at the speed of the light is the photon, which has 0 mass. And by the way, gravitational waves too, okay? The only particle that travels is the and gravitational waves as well. Gravitational waves as well, okay? Now that we have finally observed a gravitational wave, which was a prediction made by Einstein back at the beginning of the 20th century, 100 years later, we finally got experimental evidence of the existence of gravitational waves. And let's take a look at the internet, you know, the speed of gravitational waves. Okay, 300,000 kilometers per second. Gravitational waves travel at the speed of the light, okay? General relativity, experimental evidence, the detection of gravitational wave from the merger of 2 neutron stars by the LIGO and Virgo detectors confirmed that they travel at the speed of the light. That was a recent discovery, recent measurement. Okay? And we should expect a Nobel Prize for these measurements. Let's see, Nobel Prize. Let's see if they have already, I don't think they have already won. Nobel Prize, gravitational wave Nobel Prize, let's see. Oh, it was 2017, it was recent. Okay, so those guys won the Nobel Prize in 2017. MIT, Caltech, and Caltech. Okay, so those guys are next door to LA Harbor. Caltech is in Pasadena. Okay, and this type of measurements were made with a larger version of the interferometer invented by Albert Michelson, the same guy that won the Nobel Prize back at the beginning of the 20th century. Okay. And what else? Which other unexpected results of special relativity we have? Okay. There's another unexpected result of special relativity is called the length contraction. Now I want you folks to see, right? Here you go. Now that we know that time is not an absolute parameter in physics, right? It's now a function of the velocity, right? Time is a function of the velocity. It's not something that's an absolute parameter. It depends on the velocity, the relative velocity of your clock. When I mean the relative, dependent on the relative velocity of the clock with respect to differential A, right? Which is the same as since the clock is at rest with respect to differential B, the velocity of the clock with respect to differential A is the same as the velocity of differential B with respect to differential A. Okay? And now we found out that time depends on the relative velocity between referentials. The measurement of time depends on the relative velocity between referentials. It is no longer that absolute time is no longer that absolute concept we held until the early 1900s. And we have something like that for the length contraction as well, for the length as well. Okay, here you go. We can write something like that, length of a ruler in referential B measured with respect to an observer in A is going to be a function of the relative velocity as well. Okay, here you go. I'm going to put it like that. R for ruler. Okay? Again, length is no longer that absolute concept anymore. Just like time. Just like the measurement of time. Just like the measurement of time, the measurement of length also depends on the relative velocity between referentials. I didn't prove that yet, okay? But I'm going to prove that to you. Okay, I didn't prove that yet, but I'm going to, but just keep that in mind, okay? And the way, and what we find out is that the length of the ruler with respect to referential A is going to be less than the length of the ruler in its proper referential, which is referential B. Okay? Proper lengths, relative lengths. We have this length contraction. This effect. If you have time dilation, on the other hand, we have length contraction. So how do we prove that? Okay, how do we prove that? There's a very nice way of proving that. And let me get my slides. No, it's not this one here. Illustrations. Relativity. Here you go. This one here. That's time dilation, right? Let's see, I don't want that. Okay, I want this one here. Here's the ruler. All right, here's the ruler. And here's the proper length. But there's another way of doing that. Let's see if I can have the. Oh yeah, this one that we want. Okay. So here's the rocket that's flying away from planet A. Planet A has a referential A. The rocket is in the referential B. Okay, and this rocket is going from planet A to planet D. That's the distance that the rocket has to travel. Okay, that's the proper distance that the rocket has to travel. Okay, so here you go. The velocity of the rocket can be written down in terms. Okay, consider two planets separated by distance L and a spaceship moving at a relativistic speed V. It's not 20%, let's say 40% the speed of the light. This spaceship is flying from the first planet to the second. For you who stayed behind, you measure the length of the trip as being, right? The velocity of the spaceship is L divided by delta T. And the length of the trip would be the length, the period, let's see. For you who stayed behind, you measured the time the trip took as being, right? Here you go. Delta T equal to L divided by V. Like that. Okay? However, for the guy in the rocket, in the moving referential, he measures a different amount of time given by, right? Don't forget time dilation, right? Time dilation for the guy who stayed behind. Don't forget that. But for the guy that is inside the rocket, the time is not dilated. The time is shortened, right? So here you go. It's going to be something like that. The inverse of gamma. The inverse of gamma. But what you see right in here can be also here written in terms of the length measured by the astronaut in the rocket divided by its speed. And I'm going to call it L prime. That's what the astronaut measured. For the time to be less than delta T, right? You know, he must be measuring a different length between planet A and planet D, between planets A and D. That's why I'm putting L prime here. The velocity remains the same. The speed remains the same. Okay. And now I can continue my derivation in terms of the proper lengths. Okay, here you go. And how do I get the derivation in terms of the proper lengths? We can continue our derivation in terms of this equation right here. And the proper lengths is going to be given by L over B when we substitute on delta T, right? Like that. And now we have this result. I proved the result already. Okay, so here you go. That's the equation that proves that we have length contraction. This V cancel out with this V. L prime stands for length contraction. L prime stands for the length as measured by the moving referential. Okay. And there's a very simple proof. And all we are doing, we are using the result of time dilation. We proved length contraction by using the result of time dilation. That's what we did. And we can here write that, here you go. We can here write that the length as measured by an observer that stayed behind relative to the length measured by the astronaut is going to be longer. Okay? If this astronaut here, if this length measured by the astronaut is 1 meter, for instance, what this guy is going to measure is going to be less than 1 meter. And all is given in terms of the, let's see here. And I'm going to here write that too in terms of gamma, the factor gamma. L divided by gamma, like that. Okay? L divided by gamma. And here should be gamma multiplied. Gamma multiplied by L prime, like that. In terms of the notation, right? That was I was using, right? This L here, L, the distance measured according to referential A, to an observing referential A. And this L prime, if I were to here write in terms of my notation, would be the distance measured with respect to an observer in referential B, right? And I'm gonna do even more. Here you go. B, and here is my velocity, speed of referential B with respect to referential A. That would be my notation, right? Notation of the book. My notation. And that's the type of illustration you must keep in mind when you derive this phenomenon of length contraction. Okay? For you who stayed behind in planet A, which is at rest with respect to planet B, right? You measure the distance from A to B as being L. However, for the astronaut in the spaceship, he measured distance L prime, which is less than L by a factor of 1 over gamma. So what we have so far, what we have covered so far, what time is that? 10:36. We're almost there, right? Here you go. Sections of the book covered so far. Events and inertial referential frame of reference or reference frames. The postulate of relativity, time dilation, length contraction. Okay, we didn't cover relativistic momentum yet, but we're going to do that next. But before we do that, let's take attendance and go ahead, try to digest everything that we mentioned here. It can be rather difficult to admit that because that's not the world that where we live. Okay, we don't see that in our real life because we're never moving at relativistic speeds. The speed that we are used to are non-relativistic speeds. If we lived in a different universe where everybody would move at relativistic speed, then it would be rather second nature to us. But relativity is not second nature to us because we don't live in this universe. We need to make specialized type of measurements to have something like that being second nature to us. Okay, today is the 19th, right? Abir Ahmad, are you there?
Yes, I'm here.
Okay, thank you. Next is Nestor Alvarado. Let's see, Nestor. Nestor seems to be here, but I don't hear from Nestor. Next, Monte Ambarshian. I don't see Monte here. Next, Isabella Ballesteros. Isabella Ballesteros. Doesn't look like Isabella is here either. Next. Justus. Are you there, Justus? See, Justus B. Yeah, okay, thank you. Benjamin Carvajal. Thank you, Benjamin. Elizabeth Castellano.
Here.
Thank you, Elizabeth. Natalia Cordoba. Can look like Natalia is here. Jacqueline Delgadillo. Are you there, Jacqueline? Doesn't look like. Jenny Diaz.
Here.
Thank you. Valerie Diaz. I don't see Valerie either. Juan Escalera. Thank you. Bianca Eloki. Thank you, Bianca. Edwin Gonzalez. I see Edwin. I don't hear from Edwin. Let's put a star here under his name. Eli Gonzalez.
Here.
Thank you. Manuel Hernandez. I don't see Manuel here. Next is Samantha Hubert. I don't see Samantha. CJ, are you there, CJ? Doesn't look like. Amber Lopez. Amber Lopez not here. Adeli Lopez. Genesis Lopez. I don't see Genesis. Mary Michaelian. Hello, Mary. I don't hear from Mary. Next is Galia Odabashian. Hello, I see. I don't hear from Galia, right? Edwin. Okay, thank you. Edwin. Edwin, let's see. Edwin Gonzalez. Next, Ramon Olivares.
Here.
Thank you, Ramon. Next is Taylor Thorne. Thank you. Next is Jeremy Pittman. Not here. Stephanie Ramos. I don't see Stephanie. Next is Leslie Rios. Thank you, Leslie. Alexandra Romanov.
I'm here.
Thank you. Jason Strait. Thank you, Jason. And Gemma Torres Navarro.
I'm here.
Thank you. Let's see here how many students we have. 15, 19, this is the same. Was not called. Let's see.
I'm here, Professor.
Who is that?
Lester?
Can you type there in the chat window, please? Genesis.
Whoa.
Genesis, let's see. Genesis. I need to, oh, Genesis Lopez. Okay, good. And what's the other student too? I didn't get his name. Nestor, okay. Nestor, Nestor Alvarado, right?
Yeah.
Okay, 19, let's see, 17, 18, 19. What about Mary and Galia, right? Or Galia? Are you there? Okay, so let's get into our break. Break, 10:45 a.m. to 11 a.m. And I see you soon in 15 minutes. Bye-bye. Stop. I am back here. Now let's talk about relativistic momentum, okay? What happens to the momentum, right? We already saw, okay, we already saw what happens to time and length measurements when time and length, when they are measured from a different referential. And there you go, measure. Don't forget, special theory of relativity is about measurement. It's how you measure things, okay? That's what special theory of relativity is all about. We already saw what happens to time and length when they are measured from different referential. Now, let us see what happens to linear momentum. Okay, and if you want to learn a little bit more about that, I highly recommend that you look at those 3 videos from the Mechanical Universe series, episodes 42, 43, and 44. Okay, here you go, episode 42. Let's just
the time in the moving frame.
That's
how can two people moving in relation to each other
related to its coordinate in a fixed frame by
that's the Lorentz transformation that we're going to cover as well. Okay, and then that's a 42, and then we have this other one here. Let's take a look at this one here.
Yeah.
Here you go. That's velocity and time. Okay. They have this very nice graphics.
Okay.
Take a look. You know, here is what happens to events that are seen to be simultaneous in one referential, but it's not in another one. Okay?
At all. And that's the essence of it.
And here's the moving referential, right? This guy here is Einstein. This other one here is Lorentz. And we have this other one, number 44. I highly recommend so you can understand better the consequences. Let's see, I want to skip that, man.
Vai ser mais difícil do que tudo.
Oh, here you go. We're skipping. Here you go. That would be the length contraction.
The difference between moving and standing still depends only on who's doing the looking.
Oh, actually, this one is momentum.
But
okay,
when two balls collide,
yeah, like I said, I highly recommend those 3 episodes if you have time. And here you go. Relativistic moment. What happens to the momentum in relativity theory? We know that the linear momentum in Newtonian mechanics is just given by the mass times the velocity of the object. This n here represents Newtonian, okay? This n here, I'm going to put here, Newtonian theory. What happens to this momentum in relativity? We know that whenever we set the net force applied to the object, we have conservation of linear momentum. Okay, so the situation is like that. if net force is equal to 0, then initial momentum is equal to final momentum. Don't forget that net force is equal to ma, right? Which is delta V over delta T. So far, what you're seeing right here is just physics 6, okay? And when we break down delta V in terms of V minus V naught and multiply M for each one, we do get final P minus initial P is divided by delta T is equal to 0, right? We have conservation of linear momentum, conservation of linear moment, in other words, right? In other words, conservation of linear momentum is just a consequence of Newton's second law for net force equal to 0. That's what it means. So if we want, if linear momentum is to be conserved in relativity, okay? If linear momentum is to be conserved in relativity, and by the way, and very important, in both referentials, okay? Both referentials A and B, we must redefine linear momentum. So in order and the way we redefine linear momentum is in terms again of the gamma factor, okay? Here you go. We must multiply the gamma factor by the linear momentum. Okay? People usually interpret that as if the mass is increasing as it travels high speed at relativistic speeds. That's how people usually interpret that. That's why I separated the mass. Here what we have is the rest mass of the object. And now we have this relativistic mass. That's the gamma factor multiplied by the rest mass. Remember that. Under this definition, okay, linear momentum, relativistic momentum is conserved on both referentials A and B. A and B. Okay? Okay. And here you go. And this situation, let's see if I can get a drawing here for this. Yeah, I don't have it. Okay. Yeah, I don't have an illustration, but So if you use the above relation, okay, we find the following. Whenever the net force applied to an object is 0, here you go. The numeric value, of relativistic momentum measured with respect to referential A is still different from the numerical value measured in referential B, just like in mechanics. Okay, however, for this specific relation, relativistic momentum is conserved in both referential A and B. I can illustrate that better here for you. Here you go. Let's use this. I'm going to use this one and 45, right? I'm going to use this. Let's see here. No. Yeah, I'm going to use this one here. This drawing. And let's go to 45. Referentials A and B. Observer in A, observer in B. And I don't need the light clock now. In this case, I don't need the light clock because I want to illustrate the phenomenon of linear momentum. Okay, here you go. I don't need that. I don't need that. I don't need that. Okay? But I'm going to need that here. Particle P. Particle P is somewhere here in space, you know. So here you go. And we have its velocity, relative velocity with respect to A. But we also have its relative velocity with respect to B that's going to be different. Okay? Particle P. They are both observing this particle here. So we are going to have Vp with respect to A, Vp with respect to B, okay? Vp with respect to B. What else we are going to have? We are going to have, and here I am assuming that the net force is equal to 0. I'm gonna, net force applied to this particle is equal to 0. Net. Like that. Net force applied to this particle is equal to 0. So we are going to have that the momentum with respect of the particle with respect to referential A is going to be relativistic momentum, okay? And we're also going to have this other relativistic momentum with respect to particle B. They are not going to be equal. They will be different. And I'm going to state that in the next let's see, not equal. Let's put different, right? Different of the linear momentum of particle P with respect to referential B. However, in both cases, However, in both, however, linear momentum is conserved in both referentials. Okay? Linear momentum is conserved in both referentials if it's given by that relation that you found. So I'm going to put that in terms of the notes there. And by the way, I'm going to make it the most generic possible vector velocity, okay? It doesn't have to be parallel to the x-axis. Can be, you know. And don't forget that the vector velocity with respect to referential B can be a different vector. I'm going to put that like that. Here you go. Most generic possible. And this one is going to be red 2. Let's not forget that's still a vector, right? PB. Okay, oops. Not what I wanted. Here you go. In other words, if net force is equal to 0, okay? If net force applied to a particle, particle P is 0, or, right? Or, net, and I'm gonna specify apply to particle P, okay? Is equal to 0. Then initial momentum with respect to referential A is equal to final momentum with respect to referential A, and initial momentum with respect to referential B is equal to final momentum with respect to referential B. However, those two momenta separately, they are not going to be necessarily equal to each other. And that's what I'm going to put a different sign here. Here you go. Okay? Where, you know, momentum is written down in terms of this relationship here. Okay. This term in boldface is usually referred as relativistic mass. The term in boldface is usually referred as relativistic mass, implying that the mass increases and moves faster and faster. It's not that the mass increases, right? It's not that the mass increases, implying that the mass as measured by an observer in referential A. Okay, and I'm gonna put here momentum of point P with respect to referential A, right? Velocity of point P with respect to referential A. Oh. With respect to referential A. And here's the same thing, right? Velocity of point P with respect to referential A. And then we can have the same thing for referential B. The term in boldface is usually referred to as relativistic mass, implying that the mass as measured by an observing referential A increases as the speed of P increases. Okay? So now I'm gonna repeat what I have been saying, right? About the surprising results of relativity. Speed of the light is the same in any inertial frame of reference. Whether the referential is at rest with respect to light source, moving towards or away from it, the speed of the light that's measured in these three different referentials will always be the same, 300,000 kilometers per second. This is one of postulates of relativity. Two identical clocks, one at rest with respect to u, and the other moving at constant speed. The clock at rest with respect to u in referential A is clock C prime. The clock moving with respect to u in referential B is clock C. Using the above postulate, we find that the time as measured of the clock C as measured from referential A is greater than the time of clock C as measured from someone with referential B. Okay, so time dilation. The phenomenon of time dilation. The phenomenon of time dilation. Okay. Another interesting consequence is that events that are simultaneous in one referential are not, right? Are not simultaneous in another referential. Length contraction and relativistic mass increases the velocity, whereas Newtonian mechanics mass, whereas the mass in Newtonian mechanics does not change with velocity. In other words, the mass depends on the relative velocity. Okay. And we have one more interesting, okay, here you go. Those are the chapters, right? In the book. Now we're going to talk about the equivalence of mass and energy. Okay. Okay, in Newtonian mechanics, objects with mass and concepts that have no mass whatsoever, such as energy, okay? Energy has no mass whatsoever, such as energy, are independent of each other, okay? A mass may have some energy, kinetic or potential, and this energy does not add any mass to the object. Okay? Furthermore, there is both. There is no relation between them. Okay? That's not so. That's not so in relativity. Okay, in relativity theory, Einstein, right, found that a mass at rest has energy that can be tapped, from, okay? And that the famous formula of Einstein, okay, that's given, and we are talking about a mass at rest, okay? Energy, a mass at rest has some energy. It doesn't have to be moving, it doesn't have to be higher in a potential, here you go. And the relation is this one that you see right in here. And how did he derive that? We derived that in more advanced courses, okay? In courses that uses calculus-based physics course. Okay. Most of the derivations that we have so far, all you need is algebraic algebra, right? All we need is algebra, like the light clock, the time dilation, length contraction, okay? But in this case of the equivalent mass, yeah, we do need the calculus, we do need integrals, we do need differentials, okay? And the final result is something like that, actually. It's something like that, okay? But don't forget, Einstein found the mass at rest. Let's not forget. And what you see here is a huge amount of energy. What you see here is a huge amount of energy because we have the rest mass multiplied by the square of the speed of light, which is already a very high value. That's the whole principle of the atomic bomb, or even of atomic energy, okay? This is the whole principle of the atomic energy and bombs. Atomic / nuclear energy and bombs, okay? Atomic bomb or nuclear bomb. There's a difference between one and the other, okay? Atomic energy uses the splitting of the nucleus of an atom, Okay, this splitting is called the fission. When you break apart, okay? When you break apart a nucleus of the atom. Nuclear energy refers, atomic energy refers here to the splitting of the nucleus of an atom. It's also referred as fission. Fission energy, okay? Nuclear energy refers to the fusion of two nuclei, of two different nuclei, also referred as nuclei, also referred as nuclear fusion. Okay, so there is nuclear fission and there is nuclear fusion. Okay, note the difference. Note the difference between nuclear fission and nuclear fusion. Okay, nuclear fission is achieved by a bomb of plutonium, for instance, whereas nuclear fusion is achieved with a hydrogen bomb. Okay, hydrogen bombs, for instance, nuclear fusion in hydrogen in plutonium bombs, for instance. But how Einstein derived that? You know, how Einstein derived the above equation. Okay, so the step-by-step is the following, okay? The step-by-step derivation is the following. I'm just gonna give in a qualitative way, okay? The step-by-step procedure is the following. First, we use the definition of network. Remember the definition of network in physics 6, right? The work done by the net force, right? The definition of the work done by the net force. We got something like that from the work kinetic energy theorem, okay? The work done by the net force is the net force multiplied by the displacement of the object. It's possible to prove, right, and that's going to be the work kinetic energy theorem, that the work done by the net force is the difference in kinetic energy. Final kinetic energy, initial kinetic energy. This work can be either positive or negative. It all depends if the force is doing negative work or positive work, okay? So that's what we do the same in relativity. We use this formula and then we go for the next one, the next step. Then we go ahead and we replace the delta P over delta T in the equation for the net force. Okay? But in this case, it's going to be the relativistic momentum. Relativistic momentum, okay? After some higher level derivations that involve differential and integral calculus, okay, that involve differential integral calculus, we end up with the following formula. Okay, that relativistic energy is going to be given by this factor here, right? The relativistic mass times c squared, gamma mc squared. Okay, that's what we get. If the mass is at rest, we get that value that you saw before. If the mass is at rest, right? This term is going to be 0, and we get the energy of a rest mass, of a mass at rest, mc squared. So we can calculate, and now that we have this formula here, we can calculate what would be the energy of the rest mass, of a 1 kilogram mass. We get 1 kilogram, place it right in here, multiply by 300,000 kilometers square. and we get this huge amount of energy. But then we have got to make sense of this value. We have to make sense of this value, okay? How do you make sense of this value? Okay, we have to compare this value with, for instance, the amount of energy that many houses spend during a month, okay? We can do that. We can calculate that. Okay, how many houses can we power during a month, in a given month, with this amount of energy? There's a very nice back of the envelope calculation that we can obtain to find out how, what this energy is all about, okay? Just this huge number is a big number, yes, because it has 10 to the 16. But what does it represent exactly? Oh, let's see how many houses we can power during a month with this amount of energy. The average house spends roughly 400 kilowatt hour per month. Next time you go home, check your electricity bill, okay? And 400 kilowatt hour per month is a good value to be guided by. And then we gotta change this 400 kilowatt hour in terms of joules. Okay. If you're like me, I spend much more than that. I spend 600, sometimes goes to 800 kilowatt hour. Okay. Especially during the summer months. Summer months spend lots of energy on the air conditioning. So we can go ahead and, come up with the solution, right? And the way, let me get this one here. And the way we do like that is, here you go. It's just a roll of three, right? Here you go. One house spend 400 kilowatt hour in 1 month, right? So X houses spend, right? I want this one here. Nine times 10 to the 16 joules. 9 times 10 to the 16 joules per month, right? Well, we still have to change kilowatt hour in joules. I'm gonna cancel out month with month. Okay, here you go. There's a very easy way to change that. Kilo is 1,000. Okay, so I'm gonna change that kilo with the factor 1,000. Here you go. Watts we change to joules per second, right? And hours has 3,600 seconds. Make sense, right? And we can start canceling things up. Okay, this second cancels out with this second. And now we have just 1,000 joules upstairs. This joule cancel out with this other joules downstairs. 10 to the third power to the 3 power cancels out with 10 to the 16. Okay. We want to find the number of houses that you can power in 1 month with that amount of energy, with the amount of energy of a 1 kilogram mass. That's what we want, okay? So we have to invert that to know the number of houses, and I will raise that to the -1. -1 here, right? I don't need that anymore. I will invert this thing. 9 times 10 to the 13 is gonna go upstairs. 400 times 3,600 is gonna go downstairs. And I don't need the -1 power anymore. And now we can start thinking in terms of the order of magnitude, right? So here you go, 400, 1, 2, 3, right? I'm gonna put 3.6 here. So we are talking about 4 times 10 to the 5th power, right? It's 4 times 3.6 times 10 to the 5th power. 5th power here. That was 400,000 is all about. 4 times 10 to the 5th. We can cancel 10 to the 13 with 10 to the 5th, right? We cancel that. Now we gotta do this calculation here. That's around 12, right? Let's get here, calculator. Four times 3.6. Four times 3.6 is 14.4. Here's 14.4. 14.4. 9 divided by 14.4 is 0.625. 0.625. 0.625 times 10 to the 8. And look at the number of houses that we can power is just 1 kilogram mass. If we manage to convert all its nuclear energy, all its mass into energy, right? It is 6.25 times 10 to the 7, right? 6.25. We are talking about 6.25 10 to the 7. Hopefully I didn't make any mistakes. And we are going to fill in all the numbers here. 1, 1, 2, 3, 4, 5, 6, 7. Look how many houses. 1, 2, 3. I'm gonna put the 62 million and a half houses, 62.5 million houses in a single month. Okay? Now let's see how many houses we have in the United States. Let's see if we can power the whole country with just 1 kilogram, with just 1 kilogram mass, right? We have 300. What's the population of the US? Let's say here. Population of the US. 340 million people, right? roughly, in the United States, we have 340 million people, right? 340 million. Let's say we have 4 people in per house. Okay, let's say you have 4 people per house. We're going to get an average number of houses in the United States. It's going to be almost 100 million houses. Almost 100 million houses, right? 340 million. 1, 2, 3. 1, 2, 3. It's going to be 80 million, 85 million houses. 85 on the average. We have 85 million houses in the States, in the US. So we can power the whole country in a single month with 1 kilogram mass. Okay? With 1 kilogram mass, we could, in principle, power almost the entire country, the houses, right? Power the houses. Let's see, 62.5 divided by 85. Let's be more precise here. 62.5 divided by 85. We can power 73% of all houses in the United States with 1 kilogram mass, okay? 1 kilogram mass of nuclear energy. The nuclear energy, here you go, the nuclear energy of a 1 kilogram mass, can in principle, power 73%, 74%, can in principle power 74% of the houses in the US during an entire month. That's a huge amount of energy. The reality is that we need far more than 1 kilogram to power all the houses in the state, right? Because we are not using nuclear energy. We are using chemical energy. That's the type of advantage that we can benefit from nuclear energy. This is the type of advantage we can get from nuclear energy. Okay. And 11:50 right now. Any questions about that? So let's have our break again. Break 11:50 a.m. to 12:05 p.m. Okay? And I see you in 15 minutes. Thank you. See you soon. Stop sharing. Okay, I'm back here. Okay, so think about that, right? About this result that we got. Just 1 kilogram of nuclear material can power 74% of the houses in the US during a single month. And if we're talking about the regular thermoelectric power plants, you cannot do that with 1 kilogram of fuel, okay? You just cannot do it. You require far more than that. So when scientists looked at this result obtained by Einstein, they realized how They realized that they could tap into this energy, right? To either power the entire country or create weapons of mass destruction, of immense destructive power. Then the atom bomb or fission bomb, and the hydrogen or fusion bomb. In the case of the nuclear fission, okay, a single atomic nucleus is split into two. That's what fission is about. Is all about. Okay, it's breaking a nucleus into two. The difference between fission and fusion, right? In the case of nuclear fusion, you get two separate nuclei and you combine into a single one. You fuse the two nuclei into one. Fission, you split one nucleus into two nucleus, into two nuclei. Now let's keep on working on the result that we got for the energy, right? Here we go. That's the equation of the relativistic energy that you want. It's not difficult to memorize it, right? If you remember the rest mass, all you have to do to get the, that's the rest mass, right? MC squared. If you remember this rest mass, all you have to do to find out the energy as a function of the velocity is to multiply by the factor gamma. Okay? If you memorize the energy of a mass at rest, right? Comma, you can easily find the energy, the relativistic energy of a moving mass by multiplying the above by the gamma factor, right? Like that. I'm gonna put right in here, and I am going to emphasize MC square. So it's not difficult to memorize that. Not difficult to memorize this energy. Now, what about the kinetic energy? Let us get the result now. Let us use the above result. To get the relativistic kinetic energy. Okay, we are assuming that there is no potential energy. We're assuming that there is no potential energy. Okay? So how do we get the kinetic energy? Okay, the kinetic energy is going to be, since there is no potential energy, right? So the kinetic energy is going to be the moving relativistic energy minus the rest relativistic energy. Simple enough, right? So we go ahead and gamma MC square minus MC square. Okay? And we can put MC square in evidence. We get the number one right in here. We do not need this term. Okay, and we're going to factor. I'm going to get the gamma, expand the gamma factor, right? Is 1 on the top of that. That's what we get for the kinetic energy. In your book, let's take a look at your book. Okay, in your book, he presents to you the Taylor expansion of this term, of the gamma term here, okay? In terms of the V square over C square. Here, let's say, is the first order, let's say, it's the second order term in terms of second order term in terms of V over C. That's the fourth order term in terms of V over C. Or let's see, the first order term in terms of V square over C square, okay? The second order term in terms of V square over C square. Let's see what we get. Okay, that's a type of expansion that we do when we study Taylor expansion of Taylor series. Okay, or even we can use also the so-called binomial approximation. Okay, you can also use the binomial approximation to get only the first two terms. But that's exactly, there are more terms, okay, but we are not going to do expanding. Here you go. Expanding the gamma term in terms of V over C, in terms of powers of V over C, okay? We get something like that. And then you can double check that with to see if this thing really works well, okay? I can prove that to you, it works very well. Here you go. 1 divided by this square root is this term right in here. Don't forget that we have a minus half there at the top, right? Because this power right in here is downstairs. Look how they did the expansion. We preserve the first term, right? We sum with this minus. I'm going to put it here in terms of different colors so you know where each of those terms are coming from, okay? Here you go. This power here in red goes right in here. This term that you see right in here, I'm going to put that in brown. No, brown doesn't look good. Let me put it in another color. Yeah, is this term right in here, right? This term that you see here is also comes from this other one. Okay, but it's a fancy one. It's you use the minus half to get to this 3/8. Okay, let me put that in the same color, red as well. It's not going to be the same number, but you use this power to get, you use this numeric value to get this result right in here. And here is my other term. First power, second power, third power, fourth power, and so on. Okay? Now, if you go just to the first order approximation, what do you get? Using the first order approximation only, right? Very soon I'm going to prove to you that this term here is a very good approximation of what you see here. Using the first order approximation, we get the following result. And now, here you go. Notice that I'm using the approximation sign, right? And look, we're getting something like that. I'm going to here write it.